Hello, AP Computer Science A. This is our first asynchronous lecture together. We're going to start to hate the word asynchronous here in a little bit, I'm sure. But either way, we're going to talk about programming in general and why we chose Java as the language for this course. So let's talk about what computers are and what computers aren't. First of all, computers are a couple things, and they're not much better than us in any particular way, but they are computationally faster than us. They can make simple arithmetic done lightning fast, whereas we need time to process certain information. They are vastly more accurate with the number of digits that they can go out to and what they can accomplish in said time. And they are far less forgetful. The information that they store and the memory they have is an exact duplicate and perfect representation of what it once was. For us, we tend to fill in blanks with our imagination and build concepts around what we believe to be true. But what computers aren't is they're not smart. They can only do what we tell them to do. So when you get into your program and it's not working the way it's intended to work, it's not the computer's fault. It's our fault as programmers as to why it's not doing what it's supposed to be doing. It's not really a thinking machine. I know some of you might argue with me in terms of artificial intelligence and machine learning, but there's still a program behind it that's telling it how to learn and how to make decisions and do certain things. And it can get better at making those decisions, but there's still software behind it that tells it how to grow and how to learn. And so we are still the smarter individual, and the ways that we tell it to do what it's going to do is always going to be how it does what it does. So how does a computer work? Well, everything's based on a series of electrical impulses. Everything in a computer is based on these electrical impulses. So think about them as light bulbs, and they're going on and off in certain sequences. You can have an arrangement of, say, 8 light bulbs, which is it's considered 1 byte of memory, and each byte or each little individual digit is considered a bit. You've probably have heard this binary information. It has 2 states, binary being 2, an on or an off, and we represent that a lot with ones and zeros. So right now what you have here in front of you is a byte of memory in which I have 2 bits turned on and the rest of them turned off. And this could represent something in the computer. It could represent a number, it could represent a character, it could represent a color for a certain pixel on the screen, or the frequency for an audio signal, or whatever it might be. It can represent all sorts of stuff. But either way, that's all a computer can do, is turn electrical impulses on and off, and it all just depends on how it's interpreted. If you want to talk about it in terms of number, here is, say, the first 32 digits in our number system and what they mean in base 2, from base 10 to base 2. So in the green columns, you have all our base 10 numbers. That's our decimal number system. In the yellow column is their binary representation. So 0 is 0, 1 is 1, 2 is a 1, 0, 3 is a 1, 1. And what you'll notice is that on all the powers of 2, you get a new digit. So 0, 1, and then 4, and then you have 8, a brand new digit, and then 16, a brand new digit, and all the way down to 32, a brand new digit. It starts to roll over kind of like a car odometer. And as we get into our lecture, we're going to talk about how to translate these numbers from base 10 to base 2, or whatever base we want. It's actually fairly simple, and something you'll need to know for your AP exam. But there's a quick and easy representation of how they're working. So every digit in this base 2 represents a power of 2 in what it means. You can always tell that your numbers are odd based upon the last bit in the binary digit. If it ends in a 1, your number is odd. Notice 3, 5, 7, 9, 11, they all end in 1s, whereas all your even numbers end in 0s. That's another nice way to kind of tell where you're at. But again, we're going to go over some of this in the lecture. But not only numbers can be represented in binary. If you've taken AP Computer Science Principles, you know that everything is represented in binary, whether that is a number or a character. If we're talking about a character in a base 2 system, let's say the letter A, it's a 0, 1, 0, 0, 0, 0, 0, 1. It's actually the digit 65, and if you translate the digit 65 in an ASCII coding scheme, you get the character A, in uppercase A. And if you add one more piece to that, you get, or one more digit to that, you get the character B for 66 and the character C for 67. So there's lots of different ways to encode certain pieces. Pixels on your screen are technically done in an RGB red, green, blue color scheme. So there's a red pixel, a green pixel, and a blue pixel right next to each other if you look really, really closely at your screen. And we can shade that to have different variations based upon a range of numbers from 0 to 255, which is also the same range of digits we can get with 1 byte of memory, or 8 bits, all the digits from 0 up to 255. So there's lots of different ways that we can interpret this binary scheme. Okay. In terms of the bits and how they're arranged, you should know that a bit is simply a binary digit. That's where the word bit comes from. Bi for binary and the T from digit. It's represented with an on or an off, and usually with a 1 or a 0. 0 meaning off, 1 meaning on. Now there's some representations where we start stacking bits together and we can get different amounts. A nibble is 4 bits. We don't really use that, but it is true. 1 byte is 8 bits. 1 byte has 256 different numerical combinations, so the numbers 0 through 255, we're talking about all positive digits. 2 bytes of memory, if we just double it, we don't just double the amount of numbers we get. We increase it by a huge amount. We get 65,000 different numerical combinations, which is insane. And when we introduce more than 2 bytes, like say 4 bytes or 8 bytes, when we start talking about different things, we get huge amounts of information that we can represent. ASCII too is the one of the character encoding schemes that you can use to store characters. It generally uses 1 byte of information to store a character. If 1 byte has 256 different combinations, then there are, roughly 256, less than 256 different keys on a keyboard. Now that used to be true. It's not so much true anymore with all the different character maps and function keys and shifts and things that you can make on a keyboard. You can get over 256 different combinations. So we actually moved to another variation called Unicode that uses 2 bytes of memory for each character, which gives us 65,000 different combinations. So plenty of information to work with, plenty of different combinations to work with. Okay, let's go on to the next slide. Let's talk a little bit about programming. So a program is nothing more than a sequence of characters that build instructions that can perform a specific task. And you, as the programmer, are the person writing those instructions and making all the decisions. When it comes down to programming, even though you're typing out all that information in a specific language, it still needs to be broken down into those ones and zeros for the machine to understand. So this influential figure, Grace Hopper, was a lieutenant in the Navy, and she came up with the first modern day kind of interpreter, which allowed us to write information or write code in the way that makes sense to us, but then change it so that it makes sense for the computer. So basically what she wrote was a translator, a program behind the scenes that will take what we wrote in a high level language and turn it into something a little lower level so that the computer can understand it. Now, there are 2 different types of translators. You have compilers and interpreters. Interpreters translate a program 1 line at a time from start to finish, and a compiler will translate an entire program all at once, basically, before it starts to run. An interpreter is faster because it runs as it translates. A compiler is a little bit slower because it translates and then it runs. They both have their advantages and disadvantages. Most programming languages today use a compiler. And that's even starting to switch over to more interpreted languages. But Java, oddly enough, uses both a compiler and interpreter. So it does make it a little bit slower to process, but it does make it very efficient. So we'll talk about that in a second. There are different types of languages, obviously. We're learning Java in this class, but other languages, high-level languages, would be things like BASIC, if you're coding like robots, or if you're in robotics, you've seen so kind of BASIC. Pascal was what this class used to be a long, long time ago. COBOL is a business language. Fortran is formula translations. Is more of a mathematics language. PL1, C, C++, Java. Programming 1, we teach Python. There's all sorts of other languages out there. There's probably close to a couple hundred different languages for you to work with. And then there are other low-level languages. Those low-level languages would be something very close to binary code, so like machine code and assembly language. But either way, we don't code in those low-level languages anymore. We code in high-level languages, and then we use those interpreters and translators to break it down into those pieces. So then why do we do Java? Well, it comes back to that two-phase part where it has both a compiler and interpreter. So the trick here is to understand why we need the double translation almost. So let's take a trip to the United Nations here. The United Nations is a group of world leaders that all come together to make decisions and talk about policies and politics and all sorts of other things. But when you get all these world leaders together, they're all speaking different languages. And yes, this slide's a little old. I still have President Obama up here. But here's the deal. If you're going to have all these world leaders talking to each other and they all speak somewhat different languages, then you're going to need a lot of translators. You're going to need the president's going to need a translator that can translate his English into Dutch and German and Spanish and French and Italian and Russian and Chinese and Japanese and all sorts of different languages. And that seems a bit absurd for President Trump or Obama or whoever it is at the time to come with dozens of translators so that he can speak to these other leaders and then they can speak to him. If we did that, if say there were 200 world leaders, then we would need something like 20,000 translators. That's a room full of people that I just don't want to be a part of. So there's a very simple solution, and this is what Java basically uses. Instead of having each person bring a translator that can speak to every other person, what if we just pick a translator that all go to one common language, something like English? So that way, if the world leader doesn't speak English, they come in with a translator that can translate what they speak into English and from English back into what they speak. And now we all have this one common piece in mind. So now the Prime Minister of Japan brings an English translator, translates whatever he says into English, and then the President of Mexico has his English translator translate what was in English from the Japanese minister into Spanish. And the same thing works round and round. Our Russian president, he translates from English into Russian. Obviously, President Obama doesn't need a translator to go from English for anything like that. So a lot of these countries who are speaking English don't even need to bring a translator, but those who don't need to bring an English translator, and they all speak to that. Java does basically the same thing. Instead of English, it translates stuff into bytecode. And the bytecode then gets interpreted into machine code. And each machine has a slightly different coding scheme behind it. If you talk about a PC versus a Mac versus another operating system, it's off the top of my Linux, they all have a different machine code that's behind the scenes. But if we can all translate our Java program into bytecode and then we pick a specific interpreter for our machine, then we can translate that bytecode into our machine, which makes our programs platform independent. So what we do is we download something called a JRE, a Java Runtime Environment. Now, in the setup of this class, I'm asking you to download and install a JDK, a Java Development Kit, because we're going to be developing in Java. But the kit actually comes with a JRE as part of it to run your information. So what you can do, no matter what computer you're on, whether you want to code on the laptop given to you by the school or on your MacBook at home or whatever it is, you can code in Java and run it on any other machine, because what will happen is you can code it in Java, compile it into bytecode, which is similar to machine code but not quite as low level, and then your JRE, your actual interpreter, if you're running it on one machine or another, will use that interpreter to break it down even further into machine code for that specific machine. And that's what gives us platform independence, and that's what makes Java one of the top 5 languages in the world being used today, is the fact that I don't have to code it 3 different times. A lot of times when you're making like a mobile app, you have to code it for Android and iOS and whatever other devices you want to work with. When you're working with a Java program, that's not necessary. You code it once, it works, and it works everywhere because everyone has their own runtime environment. They know how to interpret the bytecode, and the bytecode file is always the same. And since then it's interpreted appropriately for your machine, there you go. So that's a little bit why we use Java. The major reason we use Java in this particular class is because the College Board tells us to, but Java has its advantages. Now, being both compiled and interpreted does make it a little bit slower to run, but with the programs we're going to write in this class, you're not going to notice any speed differences anyway, so it won't be that big of a deal for us. Other languages have other advantages like speed, C++, very fast, okay? but also a little bit more complicated to code and write in. So Java is a little bit easier, even though a little bit longer of our language to write. So we're going to give you some examples as we get into class, but that's kind of the rundown for why we chose Java and how we get some of our programs to actually run. So take a minute to like the video, comment if you need, and subscribe to the channel, and we will see you in class.